Okay, so lesson 31, the Bohr model of the atom. All right, so we've done a bunch up until this point, and really now what we're going to do, we're actually going to start putting it all together, because this model is actually, it's not the final model, but it's actually pretty close, and actually it's really useful is the biggest thing. This model will actually look familiar to anybody who's taking chemistry, because this is actually the model that you typically use when you're doing chemistry. Is called the Bohr model of the atom. Yeah, so up until this point, let's think about what we know, right? So the big one, one of the big ones was the Rutherford gold foil scattering experiment, right? And if you remember why that was important, that experiment was the one where that Rutherford shot alpha particles at gold foil. And the big takeaway from that was that most of the mass was all centered at was at the center of the atom, and it was positively charged, right? So Rutherford came up with a planetary model that looks something like this, right? Where it was, you had, let's say, a proton sitting in the middle and then the electron orbiting around the outside, right? And as you got more electrons, they would all have their own orbits, but it was pretty much like a little solar system. So this idea was popular because they knew that there was a nucleus at the center of the atom, right, with protons and neutrons, and there was electrons going around the outside. So, and it's just kind of elegant too, right? We think, okay, well, we've got solar systems on the big scale. So then if we shrink everything down, kind of makes sense that we'd have tiny little solar systems are what atoms are, right? So the problem with this, though, at the time, you guys have already seen this list, right? Here's the problems with the planetary model of Rutherford's, was that did all of the electrons travel in the same orbit, right? Why weren't they bumping into each other? Why weren't they hitting each other and knocking each other out of orbit like planets do in some solar systems, right? Especially new solar systems, they do hit each other. Ours is stable now because they've cleared paths and everything, but why don't some of these electrons hit each other, right? Two, from the known bonding characteristics, how are the electrons involved in this? If they're just orbiting around the outside, then how are the electrons like knowing each other are there, and why do they stick together, right? Like, why would, it's like two solar systems coming together and becoming like one joined solar system. Why would the planets have anything to do with that, right? Like, it doesn't, that part of it doesn't make much sense. Number three was, why do the positive protons stay together in the nucleus? So we've got, this is a picture down here of like helium, right? So you've got like one proton. But if we had, let's say, sorry, this is hydrogen, sorry. Let's say that if we had helium, then what's keeping those two positive things together, right? Positives repel. So why would they be stuck together? We're not going to figure that one out until later, but that's another question. But then the one that the Bohr model is really going to address is this one. And what this was from lesson 24, we talked about how if you had, let's say, an electron that was going around in an orbit, then remember from circular motion, that means that this thing is accelerating inward. So if you have an accelerating particle, then it emits electromagnetic radiation, right? That's what Maxwell said. And if you're emitting radiation, then you're letting energy go, right? Like, energy is leaving. You're sending off this energy out of the system. And then that's going to take away really the speed of our particle. So it's losing energy. So it's going to get slower and slower and slower until the thing just spiraled into the center and ended up right on top of the proton. But we know that doesn't happen, right? Like, atoms are pretty stable. Like, this would happen in like a flash of a second, right? But that isn't what happens. So the Bohr model is going to address this. Okay. So what scientists start to do is they want to look at really the hydrogen atom. So remember, the hydrogen is the simplest atom that is one proton with one electron orbiting around the outside. Okay. And in physics, the study of the hydrogen atom is very important because it's the simplest atom, right? You got one proton, one electron. Let's figure out how those things interact. And the reason why they didn't want to start experimenting with, let's say, helium. So helium would be like two protons and 2 neutrons, and then you've got like an electron, 2 electrons going around the outside, right? Now, if I was to study helium, well, there's some problems here, right? So if I was thinking, okay, what is the interaction between this electron and this proton, right? Like what's the binding energy or what's the force of attraction? Anything that we might want to do in physics, right? Well, that gets a little bit more confusing if you think about, okay, so this electron is negatively charged. This is positively charged, so they would attract you, right? Well, there's also this other electron hanging out here that is negatively charged. So that thing would actually repel that one, right? So now that's actually going to change the force on this electron quite a bit, right? And depending where the electron is, that'll make it different too, right? So even if we just added one more electron and one more proton, that made this system really complicated and very hard to understand, right? And I think it's worth, I'm just going to bring up a video here to kind of show you like what I mean by complexity. This actually gets into an idea, this won't be on the test or anything, but of chaos theory, where if you get a system with like, you know, a few moving parts at the beginning, so like let's say multiple electrons, multiple protons, then it becomes very difficult to understand how that's going to be sometime later, right? So if you took an atom like gold with lots of protons and electrons, right, then it's going to become even more complicated. And I'm going to show you guys just a little video here to kind of show you what I mean. So if you look at this pendulum in this video here, well, a pendulum's pretty simple, right? You get a pendulum and it swings back and forth, and we can understand how that works. But if we do a pendulum, it's called like a double pendulum. So you got a pendulum on a pendulum that you'll see in a second. Then it gets really complicated really fast. And you can't explain it. So here's just a simple pendulum, right? So this is something that we'd like to do in physics because we can understand how a pendulum works. We did this in physics 20, right? So that was a simple pendulum. And now here's a double pendulum. So it's a pendulum on a pendulum. And good luck trying to figure out the physics of that, or like the math of what's going to happen sometime later, right? So it just becomes very complicated. All right, so why I bring that up is I think it is important to understand why scientists, why people in physics want to just study this, right? Just hydrogen. That's like a simple pendulum, right? That's like one proton, one electron. There's like really only like one force or one energy going on there, right? Once I start adding more electrons and more protons, it's like the double pendulum at that point, where it's like, okay, this is like way too complicated for us to actually put precise math to at this point. Okay. And I find it kind of interesting. This is kind of the difference between physics and chemistry. Because if you think about physics, right? Physics, we like to really just focus in on like the interaction between a proton and an electron, right? And in chemistry, you're not only talking about adding more protons and electrons and everything, right? You're actually talking about adding more molecules together. So think about how complex though that would get when you've got forces on forces, because now you've got like another atom, you know, over here, right? And these things are interacting. You got electrons and you got like, and those ones are affecting those ones. Like it just turns into a crazy mess, right? So quite often physics is actually referred to as the simple science. And it doesn't mean that it's like easy to understand. It means that it deals with trying to like get to the fundamental thing that's happening, right? What's the simplest version of this thing? Let's look at that and then kind of build our knowledge from there. And then chemistry kind of looks at a bit more complex, right? Like adding together different molecules to, or different atoms to make molecules, right? And see what's going on there. And then biology is even more complex, right? Because biology is actually talking about like like a whole bunch of different chemistry happening, right? So it goes, physics is the simplest, then chemistry, and then bio is the most complex, is what they say, right? All right, so that was a bit of a tangent there, but I think it's worth understanding like what they do in physics, right? And why they chose to just study the hydrogen atom. Okay, so that being said, back to the hydrogen atom now. So what they were noticing was that if they heat up hydrogen or send a current through it, then you would get these distinct lines, right? This is that emission spectrum from hydrogen. and it'd be the same all the time, right? So they knew this part of it. They could see that. They could measure those wavelengths and know what they were, right? So a guy named Johann Jacob Balmer found a simple mathematical expression. Okay, so this one. You guys don't need to like know how to use this actually, but I'm going to explain, you know, how this progressed and how this influenced Bohr. Okay, but so this isn't even on your formula sheet. So anyway, he derived this this mathematical expression where, you know, you see wavelength on this side, and he had, you know, 2 to the power of 2 right there, and then n. So n was any integer greater than 2 and less than 7 in his expression, okay? And then he had a constant. So it was later going to be called the Rydberg constant, but when he did it, it was just a constant. And it worked, right? Like he could throw in, you know, the number, like in our example here, he could throw the number 3 in there and then solve for the wavelength, and he would get the wavelength for the red line that hydrogen produced when you heat it up, right? And then when you put in, you know, 4, 5, 6, then you got the other colors. He was really wondering though, like why, like why do we just end at 6, right? Why do we start at 3 and why do we end at 6? That seems weird, especially for a mathematician who likes to have consistency. So it wasn't until they started to discover wavelengths in the ultraviolet range that they came up with a new equation of this. And the only difference here is that instead of this being a 2, right, there was actually 2 different integer values, or 2 different integers that are happening there. You're going to have your initial integer value and then your final integer value. Okay. And then from there, we were actually able to get a whole bunch of different wavelengths. So I'll go down a little bit. We found a bunch in the ultraviolet section, a bunch in the visible spectrum, and then a bunch in the infrared range, right? And these are called different series. So you can see if we go down a little bit, there's the Balmer series that you can find. There's the Lyman series that are in the infrared or the ultraviolet, and then you've got your Passion series that are in the infrared. Okay, so Balmer you can see, and then these ones you can't, right? So yeah, this is pretty much the idea that this was known at the time, and then Niels Bohr was going to start to use some of these ideas to come up with his model of the atom. So, and like I said here, there's just saying that you don't need to understand, like you don't need to use this equation, but just understand that this was instrumental for Niels Bohr. All right, so here's Bohr's postulates. So again, this is the data, this is the information that Bohr is going off of, right? There was a bunch of huge experiments that led up to this point. So just as a recap, remember we used J.J. Thomson's cathode ray tube experiment, where he was able to find that there are negatively charged things and positively charged things, right? That was where he was able to deflect them, and he was able to figure out the charge to mass ratio. Remember, like way back when we did that? Okay, so pretty much there though, he knew that, okay, well, these things have charge, right? We've got electrons and we got protons, okay? Rutherford's nuclear model was saying that most of the mass was all at the center, and it was the proton, right? Proton and neutron. They knew there was protons and neutrons, and they were at the center in the nucleus, okay? We had Planck's quantum theory, that energy is actually quantized. Einstein's photon theory, kind of in the same ballpark, where they're saying that photons themselves are actually quantized, right? You only get individual little packets of light or packets of energy with Planck's theory. Okay, the emission and absorption spectrum for hydrogen, so above, right, what we were just looking at. So what's going on there? Why is it those distinct lines? And oh man, this is pretty much the same thing, right? And then the Frank-Hertz experiment, remember that was the last one where you had like different electrons bumping into mercury vapor, and it would give away some of its energy and then carry off with the rest. All right, so Niels Bohr came up with different things called postulates. So a postulate is an assumed idea upon which a theory is based. Okay, so here is kind of like, if he was to break it down, his theory. So number one, you guys are responsible for knowing Bohr's postulates here, okay? So electrons move in circular orbits, but they do not radiate energy. So remember, that was the big problem from above. So if we're looking at the hydrogen atom, he says, okay, so we've got, sorry, I'm kind of drawing this at a little different angle, so my circles aren't good circles. So we've got our hydrogen atom, that should be a circle, and that's our orbit, right? So there's an orbit, and let's say here's another orbit. So we've got another one there, right? And he says, okay, well, these electrons actually just keep going around in circles, and they don't radiate energy. This one almost kind of seems like a cop-out, because wasn't that the problem, right? Like that when things are going around in circles, they radiate energy, and it's going to spiral into the into the center. And he said, well, no, they don't. They go, they're in these circular orbits, but they don't radiate energy. And you can imagine all the scientists at the time said, what, right? Like what do you mean? Like, what are you talking about? He called them stationary states, right? So it's like they're going in a circle, but they're not really going in a circle, right? It's like this weird thing going on, right? And it sounds weird and it sounds wrong. Just bear with me here. Everybody else at the time did too. So you'll be in good company. Even Einstein didn't like this, right? All right, the next one, and probably the weirdest one. Electrons can jump from one stationary state to another, but they cannot exist in between them. All right, let's talk about why that is a weird idea. He's saying that, okay, this electron could be in this orbit, or it could be in this orbit, right, going around and around, and nowhere in between, right? So it says that this electron here can jump up to there, right? But you would never find it in the middle anywhere. It's like it's here, and then it just like literally transports from there to there, right? And again, everybody said, what? You're saying this electron just like disappears from this one and just ends up in this one? Like what are you talking about, right? That's still weird. And this actually even has a name that you've probably heard before. This is actually called a quantum leap. So if you ever hear that like in a science fiction movie or anything, that's what that means. That like this electron literally does just like disappear from here and ends up there. And this sounds like we're talking about magic at this point, right? And the scientists said the same thing. They were saying, well, this sounds ridiculous, right? But he's following the logic, right? Like this is actually what is happening. Like if you look at the different experiments, he is following what the science is saying, even if it doesn't seem intuitive. All right, and again, if you guys don't like this, I've got like a little bit different way of explaining it in another lesson that'll kind of make it it'll seem less magical when we look at it in a different way. Okay, so the next part. Oh yeah, sorry. In that one, he said that the energy for every one of these jumps could be considered a jump from whatever your energy was, let's say here, and then to whatever your energy was here, right? So that'll be the energy or absorbed, right? So remember, if energy gets absorbed, then that means the electron would like jump up one level or whatever, however many levels. And if it's emitted, then that's the electron jumping back down again and then emitting a wave. Okay, so he says that energy will be the difference between those different energies of the orbit. All right, number 3, all possible orbits around the nucleus only have a few allowed. Yeah, that's pretty much what I was saying there. But here's a little bit of math to it. Is he's saying that the energy will be the energy 1 divided by n, where n is going to be our principal quantum number. So that can be like 1, 2, 3, anything else, right? So yeah, so pretty much again saying that we've got quantization happening, right? That's going to be like a 1 or a 2 or a 3 or anything else there. Okay. And then this one is the radius of the hydrogen atom. Okay, so for this one, they're saying that the radius, so the radius here for any given orbit, right? So if I've got like a proton and like there's a one there and one there, then the radius, so like how far this proton is from this electron here, is going to be determined by this equation. So you can say the radius at 2, let's say, well then it would be like 2 squared, so 4, times the radius of the atom just at its initial radius there. Okay. And sorry, maybe I didn't explain that well in the other one. So same type of thing going on in this one, where the radius or the energy at any given level, so like this would be like level 1, level 2, etc., is going to be equal to the energy at the ground state. So that's just the energy it has when it's just sitting there, and then divided by whatever energy level you're talking about there. So for hydrogen, we found that 13.6 electron volts, or that many joules, and it has a radius of that, right? And that's for the ground level, right? So that was for like 1. And that's where that electron just sits. That electron would never drop into the proton. Like it's never going to fall into it. It's always going to stay in that like E equals 1, or that ground state. All right. So kind of interesting here. Niels Bohr was actually terrible at writing. So he, like an absolute genius, he couldn't get his ideas on paper. And this was a big, like, he had to overcome this. He actually had his wife that helped him out in a lot of ways, trying to write down his ideas, because he just couldn't really do it. And I find this kind of interesting. He said, when asked why he had such difficulties, he said, grammar teachers. So passing the buck, I guess. Okay, so our energy level diagrams. So below is an energy level diagram for hydrogen. So when I look at this, I actually always still kind of keep in mind our picture of the Bohr model, right? So every one of these different little energy levels going up and up and up, right? Those actually correspond to these energy levels going around the atom. Okay, so like this would be my ground state. That would be right here. Okay, and then right here, that's going to be my end is 2. And then so on. So as we go around, you'd have more and more and more, right? That electron can get higher and higher and higher, or farther and farther away, right? And I also want you to notice that we can look at the scale of this thing 2 different ways, right? We can think about, well, this line right here at the top, it says n is equal to infinity. Do you guys notice how these lines are kind of getting like closer and closer and closer? So you could actually have like n is equal to 10, n is equal to 20, n is equal to 100. You technically could, but they actually get kind of like closer and closer and closer until you get to a certain point when this electron is actually just barely holding on, right? There's like hardly any energy required to keep it there. So then that's actually what we call the ionization level. So at that point, when you give it, well, exactly 13.6 electron volts, that electron no longer needs to stay here. It'll actually leave and it gets ionized. That's why it's called the ionization level. Okay. So yeah, so that's what that's talking about. Now, we also need to see that we can think about the energy in 2 different ways. And we've talked about energy this way before too, with like potential energy, how we can call whatever we want the reference level. So I can call this, like the right side probably seems a bit more intuitive, right? So if you were at your ground level, then it's at 0 electron volts, okay? And then if I give that electron 13.6 electron volts, then I'm giving it its ionization level and it'll be stripped away. Okay, so that one kind of makes sense. But you can also think about it this way, that let's call 0 the ionization level, and then we start considering that everything else are negative energies. So this is so it would take negative 13.6 electron volts is where it would normally sit. And then 0 is our ionization level. So 2 different ways of looking at the same thing. We're just changing what we're calling 0. So here is 0, and then there is 0. So yeah, I know that can be a little bit confusing. It's not as bad as you think once you get going. For the most part, the biggest thing that we need to do when we start like figuring out these jumps is going to be the difference between these. So I'll show you what I mean in a second here. So like in this one, it says, in order to jump from one energy level to another, the atom had to absorb or emit the difference in the energy levels. So if I want to figure out, let's say, if we had an electron that jumped from here down to here, well, that's just going to be 13.1 minus 12.1, right? Just the difference in their energy. And if I was looking over at this side of the scale, like maybe the picture they gave us was like this, well, that's going to be really kind of similar, right? Because it's still just going to be the difference between these energies. And the difference between those energies is going to be the same as the difference between those energies. So it doesn't actually really matter. You can almost kind of ignore the negatives there because we really just need the difference between them. So you can think about it as like the absolute value between those energies. Okay, so from this though, what we can do, like we did in the last lesson, as soon as we know what the differences in energies are, then remember our just simple equations there. Energy is equal to Planck's constant times F, or energy is equal to Planck's constant times the speed of light over the wavelength. And remember, like I know some people had a little bit a tough time with this. Remember that we use a different Planck's constant based on whether or not we want our energy in electron volts or in joules, right? So just make sure you're using the right Planck's constant based on what you want to get out. Okay, so there's some examples, very similar to what we did in the last lesson though. Okay, so the idea here is this actually kind of explains our different series that they found at the beginning. So there's the Lyman series, the Balmer series, and the Paschen series. So if you can see, here's our energy level diagram. The Lyman series are all of the different jumps when the electron falls back down again and emits a wave, right? That's what we're seeing as a light wave. And the Lyman series is when they jump right back down to our ground state, right? To n is equal to 1. And the Balmer series, so things that we see in our visible spectrum, visible light spectrum, that is when things jump down to n is equal to 2, right? So remember, these things can take any path down. They could jump, to any line. So, and then you've also got your Paschen series that jump down to this one. And you actually would have other ones that would be down to this one, right? There would be like different series going on. But these are kind of your primary or most prevalent different series of radiation or of light that you're going to see, the emitted light. Okay. Now, strengths of the Bohr model of the atom. So Bohr's model of the atom could explain the size of the hydrogen atom, right? He was able to use his equation, this one, right, to figure out the radius of the atom of hydrogen, right? So mathematically, he was able to actually show that. Bohr's model gave an ionization level that corresponded to the known ionization level. So that's always good, right? So his model actually was able to say, if I give this thing 13.6 electron volts, right, or 13.6 electron volts, that's the amount of energy to strip the electron away from the atom. Okay, so it's always a good sign when your math or your model corresponds with reality, right? That's true science. All right, so 3, Bohr's model could account for the different spectral lines in the hydrogen atom. So like Lyman, Paschen, and Balmer series, right? They were able to use a mathematical expression to show, when you would get them. But the Bohr's model was able to actually describe why that happens, right? So his was a lot more powerful. And I won't get into it yet. Okay, so Bohr's model could be expanded with some modifications to account for larger atoms. So again, with his model, he could account for, let's say, helium. Oh, that's not how that works. Right? Where you had 2 electrons orbiting around. So with some modifications, he was able to actually, you could do a little bit of calculations to figure out, okay, what would the energy level be if you had 2 electrons in there? It wasn't great yet though. Like some things kind of fell apart there. Like especially when you started getting to like really big atoms and everything, like there was still a lot that wasn't known about bigger atoms, but it was on the right track, right? Like things were looking promising. And then Bohr's atom used the nucleus idea from Rutherford. So it had most of its mass at the center. Yeah. So problems though. So there's still problems. So Bohr's model only worked well for hydrogen. It like I was saying above, like it didn't, it had to be modified quite a lot to account for the bigger molecules or atoms. I mean, sorry. Bohr's model could not explain why the number of spectral lines increased for some elements when they were placed in electric and magnetic fields. Not going to get into that one, but Bohr's model was not able to explain the relative intensity of some of the spectral lines. So why some lines were brighter than other lines, right? So there's still a lot going on that he wasn't able to explain at this point, right? The big one here, I think, was probably the first one, just that it still wasn't, actually, they're all probably pretty big. It just didn't give us quite that full picture yet. And I think the other part is that just, it was weird, right? Like we're talking about like electrons jumping from one orbit to another, like teleporting. Like what are we even talking about anymore? So scientists at the time had a very big problem with Bohr's model, right? It wasn't until, well, really, that there was enough evidence for it that you started to get even Einstein, who was actually opposed to a lot of these ideas, started to come around to see that, well, actually, this is kind of seeming like it's true. Okay, so no practice problems. You guys just go straight to the hand in assignment. So